All right. Well, first of all, hello everyone, both in person and remotely. So as Costa said, I'm going to talk about the synergies that can happen between future large-scale experiments and Euclid in particular, because I'm a member of the Euclid consortium, and the benefits of the joint analysis with CMB experiments. And of course, I need to mention at first that the work I'm going to present is not just my own work, and it has been done with many members of the collaboration. I guess I don't need to tell this audience the reason why we want to combine probes together. Like this is like, let's say this is the canonical example of why we want to combine probes to get the best possible constraint on our cosmological model, and more precisely on the values of cosmological parameter. And then when it comes to figure out which probes to combine with each other, one might adopt this set of constraints to motivate which one to pick. One would be to try to cover as much as possible the different sectors of the universe. By sector, I mean on one side, probing the background evolution, so everything that has to do with standard candle, standard ruler, etc. And on the other side, you want to try to probe also the growth of structure, so the way the structure grows throughout the history of the universe. Another criteria would be in terms of epoch. You want to cover the largest possible epoch in the history of the universe. And that's where the idea of picking up the CMB and the large-scale structure survey comes up. Because on the one hand, you have pretty much the largest lever arm in time that you can get in terms of coverage of the timeline of the universe. And on the other side, both of these probes actually cover both sectors. The CMB has information about the background via the position of the peaks, information about the perturbation via the amplitude of scalar perturbation. And on the other hand, the large-scale survey have, of course, the BAO for the background and just the measurement of clustering for the perturbation. So those are two natural candidates. But there's also an additional benefits to picking up those two. If we go back to the timeline of the universe, there's the idea that between the moment the CMB was emitted and the moment it was measured by an instrument like Planck, it had to go through basically our whole, it traveled throughout the whole history of our universe, and it was influenced by all the intervening matter between us and the last scattering surface. And this has the consequence of, when doing the joint analysis of those two things together, they are not independent. There is actually a non-zero correlation between those two things via a multitude of effects. The main effect would be with gravitational lensing, which changes the path of the CMB photons and creates small distortion in this otherwise pristine fluctuations map. On the other hand, you have the integrated Zach-Zolf effect, and also its nonlinear counterpart, which is the Risch-Yama effect, which has to do with the decay of gravitational potential with time, and it gives a boost, at least in the standard model, it gives a boost to the CMB photon, which can also be detected and exploited. So those are more, let's say, gravitational ways in which the CMB photons are affected. Then there's more astrophysical consideration. One would be something like the Sunyaev-Zeldovich effect. So any effect that due to actual matter, like particle, electron, that bumped into the CMB photons and changes their energy. And on the other hand, this one is a bit more specific. It's more, it has to do more with the frequency at which we observe the CMB. The CMB is not alone at those frequencies, and you have additional signal that also create, like for example here, it's a cutout of the so-called cosmic infrared background. So those are all the galaxies you cannot individually resolve, but they are here. They form a background in your measurements, and this has to be taken into account. And this but this is not just some nuisance foreground, but it also contains cosmological information. So all of this is nicely exploitable, not just the individual combination of those two probes. So in terms of prospect, when it comes to data, well, on one side you have as current CMB survey, you have of course Planck, and in space, and on the ground you have like the Atacama gang on the top, like including ACT, and the South Pole gang on the bottom, including BICEP, SPT, and Keck. But as we move into this new decade in this the era of real precision cosmology, we move even further down in terms of stages of CMB experiment. And in the future, especially in the future, we expect a lot from Simon's Observatory on the ground. This is going to be up there in the Atacama. Lightbird, a future Japanese satellite, which has been pretty much green lighted at the horizon of maybe 2030. And even further down in this stage 4 era of CMB survey, we have the so-called CMB stage 4, which is like, of course, a temporary name, which would go even further down in sensitivity and number of detector. On the large-scale survey side, there's also in the literature a similar type of classification. That's the Dark Energy Task Force classification, with different stages, with ever-increasing precision, depth, and coverage of the sky. Stage 2 was some already finished survey or ongoing survey like SDSS and KIDS. Stage 3 would be DES, and stage 4, that's the stuff we're really waiting for, like DESI, LSST, and of course Euclid. So Euclid is going to be my main focus for this talk. A quick fact sheet about Euclid for those who are not completely aware of the details. So it's a future satellite. It's an ESA mission. It's going to be around L2. It's going to run for 6 years because no refueling possible at L2. That's like a few million kilometers away. So the launch date, that's okay. It's supposedly set in stone, but you know how those things works. February 5th, 2023. You might have seen this GWST XKCD. So when I said it's the definitive date, you can make up your mind. I tried to be funny one day, and I actually did the same kind of plot with the Euclid launch date, and you know, the same conclusion as this one, like that at least the slope is less than 1, even though there's kind of a little jump recently, but hopefully this is just a statistical fluctuation. But yeah, so Euclid, yeah. Maybe that will be of interest of you who are not part of the collaboration. Like there's a quick release which is expected after roughly 17th month, and the full first data release it's at 29 months. There's 2 instruments in there. There's a spectrometer and a visual imager. One third of the sky is going to be covered, and by the presence of those 2 instruments, basically we are going to have two survey, one photometric, so which is going to be really wide and but not the best accuracy when it comes to redshift determination. And on the other end, you're going to have a more narrow, more deep, but much more precise survey done with a spectroscopic survey. And the main 2 probes to be the official two main probes of Euclid are going to be measurement of galaxy clustering and weak lensing. All right, so if I go back to this picture, so as I said, I'm going to talk about the future joint analysis, what we can expect from the future analysis of CMB experiment, like I mentioned, those I mentioned, and Euclid in particular. And this is, to be more precise, this is actually the purpose of a working group inside the Euclid consortium, of which I am a member, which is called, quite aptly named, the Euclid CMB-cross correlation science working group, quite a mouthful, whose objective is indeed to explore and prepare the joint analysis of Euclid and CMB data, both current and future. This is going to be essentially the paper of which the results I'm going to talk about. So in case you can write down the reference, or we can discuss, of course, later on. This is the paper whose results I'm going to describe. And I have also to mention right now, and I will mention it several times, but a lot of the work that has been done here is built upon another Euclid paper of the Euclid Collaboration, which is this one, which was made. It's a paper that actually Elizabeth mentioned yesterday during her talk. It's like the let's say the official up-to-date forecast from the Euclid Collaboration about the Euclid probes. So simply weak lensing, galaxy clustering, and their cross correlation. And this is, as Elizabeth said, this is really a tremendous work. And I'm not just saying that because my name is somewhere around here. It's like really a group effort of many people Some of them are in this room with us, so a lot of the methods and rigor that this group adopted, the IST, the Interscience Task Force, we try to replicate them as much as possible in our paper. And really, the idea of this paper, of our paper, is to follow those two objectives. As I said, forecasting the cosmological potential of this joint analysis, but also serving as a basis for like the development of the actual cosmological pipeline who is going to take in the data and analyze it. All right, so how did we do those forecasts? We adopted the Fisher formalism, fairly standard stuff. You built this Fisher matrix by computing like this ensemble average of the log of your likelihood, of the second derivative of the log of the likelihood as a function of those theta, which are your model parameter. They can be cosmological parameter, but they can be also nuisance parameter. And once you obtain this Fisher matrix, you just invert it, and that's your errors of your forecasted error, forecasted covariance on your parameter. You might be familiar with this particular expression for this matrix when your observable are follow a Gaussian PDF. So, as you can see from the previous formula, the main ingredient that you have to figure out how to write is the likelihood of your model as a function of your observable. So the first thing you need, the first ingredient is to choose, okay, models, what model do we want to test? Those are the same, so we choose the same model as I said. I'm probably going to repeat myself a lot, so I apologize in advance, but a lot of those choices were motivated in order to be accompany and be like a companion paper to the IST forecast Euclid paper. So the models were chosen to be the same as the IST paper, namely on one side, of course, the standard six parameter lambda CDM. The mass of the neutrinos was fixed for this particular exercise. There might be in the future dedicated paper to neutrinos and other extended model. So for the purpose of this particular exercise, we fixed it to the 0.06 EV, so-called minimal neutrino. Extended dark energy model, we went beyond the cosmological constant by taking the classic CPL parameterization. We also introduced curvature, and we explored briefly modified gravity model via the so-called gamma parameterization, which is a phenomenological parameterization of modified gravity. Not the best, but yeah, we had to, for various reasons, we had to choose this one. Can discuss it later. Already there was like kind of something we had to be careful for us CMB people compared to large-scale structure people is the choice of parameter. We had to follow the IST convention, which of course works with like this kind of parameter, H0 sigma 8. But as you know, for CMB experiments, it's better to work in a different basis that uses, for example, theta instead of H0 or the amplitude of scalar perturbation instead of sigma 8, and also a small omega versus the big omega. And this has all to do with the idea of prior, like what kind of prior you use as a basis. There's also a small problem that had to be solved with, namely that the gamma parameterization, this phenomenological parameterization, has really been thought as something to apply to large-scale structure, like large-scale structure survey, so late universe probe and sub-horizon scale. And of course, CMB is not that at all. It's like it goes to super horizon scale and it goes super far in the future, in the past. So also something to keep in mind once we have the real data and we want to do those things. Like the issue of the choice of parameter is quite important. So the final model, 6 of them, and it's basically variation of what I said, like what kind of dark energy model, flat or not flat, gamma or no gamma. And those are the values that we chose as fiducial values for those parameter for the Fisher analysis. And yeah, it's nothing too out of the ordinary. Just a quick mention here: we didn't work with omega k like the curvature. We worked; it's purely equivalent, but we choose to work with omega dark energy as a free parameter for modeling curvature. Okay, so we have the models now. What about the observable? Okay, the observable, the main type of observable that were chosen, that we choose to work with, were the CLs, so the angular power spectrum. And in terms of what kind of signal did we consider, well, I kind of briefly mentioned it already, but on the Euclid side, we considered as signal first, as probe, the photometric galaxy clustering, then the weak lensing, and finally, as separately, the spectroscopic galaxy clustering. And you see a little star here. It's just so that to mention that the spectroscopic galaxy clustering has been considered throughout the whole analysis as a separate probe. This was done for several reasons. One of them being that the spectroscopic galaxy clustering actually speaks a slightly different language than the photometric sample, namely that it's not CLs that are typically used as observable, it's directly the P of K. And dealing with the covariance between those two types of observable is more or less still an open problem. So remember that the spectroscopic galaxy clustering is there in the analysis, but it's considered as an independent probe. So it's added at the end, like as an independent probe. A slightly more detail about the Euclid recipes that we used. We basically adopted two, well, when I say we, again, it's following the convention of the IST paper. We followed basically two cases. We adopted two cases, one pessimistic and one optimistic. And the main differences between the two was in terms of how deep we hope to go in those different scenarios, the corresponding number of redshift bin, and also the maximum multiple that we hope to reach in those two scenarios. In terms of redshift bin and redshift distribution of galaxy, you have here as a dashed blue the whole assumed distribution of galaxy. It's assumed to be fixed. There's no free parameter there. And that's the gray bands are the breakdown in terms of redshift bin in observable space, let's say, observable redshift, and the blue bell curves here correspond to the real underlying redshift distribution for each of those 10 bins. And at the end of the day, in terms of additional parameter on top of the cosmological parameter, we have, depending on the case, 5 or 10 nuisance parameter for a bias that is assumed to be linear and constant in each bin, and 3 additional parameter for the model used for accounting for intrinsic alignment in the weak lensing. So that was for Euclid. So now CMB. CMB, three types of signal considered: temperature, polarization, and CMB lensing. You'll note that here for polarization, I scratched the B modes. In this particular context, since no tensor mode were considered at all in the IST forecast paper, we choose for the moment to not account and to not explore this either. That would imply adding a new cosmological parameter R, and we prefer to stick as much as possible to the IST paper. So no B modes, no, just E modes. And of course, I just remind you that in those two signals, it's not just something that happens at z equal 1000. There's all contained inside of those signals. There's everything that happened afterward between z equal 1000 and now. Similarly to the Euclid probes, we considered different scenarios, let's say, namely 3 types of CMB experiment: a Planck-like experiment, a Simon's observatory type experiment, and a CMB stage 4 type experiment. And the way those different scenarios vary, as you can see, they vary in terms of sky fraction, size of the beam, noise level for temperature and polarization, and multiple range. You'll notice that the two future ground survey have a smaller sky fraction, but we can imagine naturally in the future that we're not going to just use those things by themselves. We're going to combine them with Planck, because Planck has, of course, less sensitivity, but it observes almost the whole sky. So the idea here is not just Simon's SO and CMB stage 4. It's a combination of those things with the large scales of Planck. So that's why at the top you see Planck low Hell. This is a brief overview of what the expected coverage of those experiments are. Namely, actually, the blue one is Euclid, and if I'm not mistaken, like the overall kind of reddish coverage is Simon's Observatory. For S4, we don't really have any idea of what the coverage will be yet. So this is SO is kind of the most defined of those yet. And on the right, it's just a noise level of all the different signal, temperature, polarization, and lensing. The different levels of noise as a function of the experiment. So this thing is sliding slowly but surely. Okay, so that was our observable. So what did we try to show in this particular paper? We wanted to show what's the benefits that comes with adding on top of Euclid CMB data. So we explored basically 3 different scientific cases, and then we saw how the constraint on cosmological parameter were evolving from one case to the other. And the 3 cases are as following. They are described, each of the cases is described as this kind of matrix. It's a matrix of observable. It tells you have all those signals that I talked about as columns and row, and all the possible spectra you can make out of it. And the matrix tells you which one, for the case in question, which spectra have been taken into account. The case number 0 is the baseline. It's Euclid only. That's what the IST paper did. And as I said, it only does galaxy clustering, weak lensing, and the cross correlation between the two. Then case 1 is, let's say, what most people have in mind when they want to use the CMB on top of large-scale structure, namely to add, to consider all the matter probe, or the matter counterpart of the counterpart of matter probes in the CMB, namely the CMB lensing, because the CMB lensing is really thought as a map of a projected map of the distribution of matter in the universe. So the most natural thing that people want to do when they say, okay, CMB plus Euclid plus CMB, is to use just the CMB lensing. So you see these 3 spectrum. So the lensing and its cross correlation with the Euclid probes are in case number 1. And kind of case number 2, that's the one where we add everything except so all the CMB probes here and all the possible cross spectra, of course excluding anything that has to do with B mode, as I mentioned earlier. Okay, a few words about the practical work that actually went into this work. It's similar, as we said, we tried to follow similar protocol as the IST group, in the sense of trying to do something very as rigorous as possible. We had a lot of people involved in several different countries. I happen to be the coordinator of this effort, and also a participant in those forecasting efforts. And this work has really been done in close collaboration with the IST group, especially when it came to the validation of our forecasting code, because we overlapped in terms of the kind of stuff we were predicting. So we went through quite an extended period of validation and extended use of classic tools in order to follow the whole development. And as I said before, all those results are compiled in the publication that I mentioned earlier. All right, so let's go to the results now. As I said, there's those 2 scientific cases. So like just adding CMB lensing and adding all CMB probes. That's the 2 scientific cases. 6 cosmological model, 10 cosmological parameter plus a dozen of nuisance parameter. We have our 2 sets of Euclid specification, pessimistic, optimistic, and 3 scenario for a CMB experiment. So that's a lot of results. Like if you multiply all of those things, you can imagine that it starts to make a lot of numbers to try, and for me to try to present them in a concise manner now. I'll try my best to distill the essential part. I flash on the screen the case 0. So what are we starting from? Like the Euclid probes, the Euclid constraint. So you have the constraint for all the 6 parameter, for the pessimistic case, optimistic case, and for all the cosmological parameter. That's actually not exactly it's not the 1 sigma error bar, it's the 1 sigma so-called precision. which is essentially the error bar divided by the fiducial value of the parameter. So it has to be basically understood in terms of percentage of error on the forecast, percentage of error on the parameter thanks to the forecast. So you see, in terms of range, you see essentially the kind of number we're starting from, which are already quite good. So, but keep in mind when I'm going to show you the improvements, because to know where we are going. So the first thing I want to show is what happened. That's the first case. So when we go from case 0 to case 1, what happens when we add just the CMB lensing? And I'm going to show results in terms of what I call improvement factor, which are really just take the error bar before adding the CMB and divide it by the new error bar after adding the CMB. So this is something you want to be as big as possible. And a value of, let's say, 2 means that your error bar basically were shrunk in half, by half. Oh, okay, so this is, okay, that's what I said, lots of number, but it's, I'll try to be as clear as possible. So basically you see you have, so this is what happens when you add CMB lensing to pessimistic Euclid. And you have basically three blocks of 6 lines for Planck, SO, and S4. And each line corresponds to one model. Each column corresponds to one parameter. You have the block of cosmological parameter first, and then the block of nuisance parameter, bias and intrinsic alignment. And as I said, the number is this improvement factor. And if we start with the modest improvement, we see already that, like, kind of as expected, let's say the CMB lensing is maybe a cleaner probe of lensing and of matter in the universe. So you can alleviate up to like a couple of, like, maybe 20% the error the uncertainty that you have on those nuisance parameter of intrinsic alignment. And also on the bias parameter, you have even a better improvement on a better handle on those pesky nuisance parameter because they really don't appear at all in the CMB lensing, so you really can break degeneracy. Of course, in terms of global trend, you see that as you go from Planck to SO to S4, the number grow, which is expected because the sensitivity goes down, the improvement goes up. And you see the biggest there's an improvement all around, but yeah, for the regular cosmological parameter, they are maybe not that impressive, although a factor of 1.4, that we mean like almost like 30–40% shrinking in the error bars, which is quite good. But they're particularly effective when it comes to extended model, like WA, so like the variation of the equation of state of dark energy, and also omega dE, which I remind you is actually a measure of the curvature. So curvature, you can get up to a factor of almost 4, reducing the error bar just by adding the CMB lensing.
So why is curvature so strongly affect outside? So why I can wait with at the end?
Yeah, I guess we could even. Yeah, okay. The question was from Stefano, why the omega dark energy is particularly useful. So as far as I could tell, I did. It's starting to date. So I have a plenty of intermediate plot that I don't have time to show, but it really has to do with the idea that it's. As far as I could tell, the fact that it probes the matter distribution over the whole entirety of the history of the universe, and it has also it's not just a probe of the matter distribution, but it has a dependency on the background as well. There's an H factor in there and volume effects, which actually, as far as I could tell, are the reason why it helps so much with this effect, and it's combined with the fact that it's one of the model with the most degrees of freedom, where Euclid is starting, the pessimistic Euclid is starting to struggle, especially since we're missing this whole range of redshift here, and so it's really a combination of those two things. It's kind of filling up the gap left here. And when it comes to, so that was for pessimistic Euclid, and of course I'm going to show you what optimistic Euclid looks like. It's much less colorful. That doesn't mean that the CMB is suddenly not doing anything. It's probably doing the same amount. It's bringing up the same amount of information, but as you remember, in terms of characteristic, the optimistic Euclid is significantly better than pessimistic Euclid. So the gains are less visible, but they are still non-negligible, especially in the extended model. So then when it comes to case number two is what happens when you compare Euclid alone to Euclid, to the full Euclid. So we go all the way, we take the time to implement all the possible cross-correlation between the two, make a proper Fisher analysis, build a proper likelihood that takes into account, that neglects nothing. And then, of course, it's the magic of the CMB comes up. I mean, not just the magic of the CMB, but the magic of the complementarity between CMB and large-scale structure immediately pops up. And especially for some of the regular cosmological parameter, sometimes you almost gain a factor of 10. So you really shrunk your error bar. You divide the error by a factor of 10, which is quite impressive and tremendous. And it's the same. You can observe the same effect for the extended parameter. In this particular case, because nothing more basically has to be gained on those parameters, so that's why they are at 1. Sorry, yeah, go ahead.
Is this symmetric? So this factor is the improvement also on the other side. So if you just had the stage 4 CMB, you would also get an improvement on omega baryon using Euclid of a factor of say 5 or something, or?
No, not exactly.
No, so this is really just coming from the fact that stage 4 pins omega baryon down.
Yeah.
To really some high precision.
Yeah. That's a non-symmetrical. Those numbers are non-symmetrical. Yeah. And the same trend. Okay, so as I said, the same trend as before. Like you really have the progression as you go from Planck to S4, and again, same trend, but still very good numbers when it comes to when you use as a reference optimistic Euclid. But you still have you especially have some nice handle on the bias parameter, because like those bias parameter, let's say in baseline Euclid, they appear squared. Okay, you have the cross correlation with reclancing, but let's say they might mainly appear as a square, but then in the cross correlation with the CMB, they appear as just raised to the power of 1. So you can get some handle on breaking degeneracy. This is just another way, maybe it's more visually striking. It's a focus on essentially this block. Pessimistic Euclid because we want to always assume the worst, and I choose SO because that's, let's say, the one that's the most likely to exist in the relatively near future. S4 is still kind of we don't know much about S4, so it's just this kind of spider plot is really a visual representation of the error bar. The distance from the center of the spider plot to the edge is the reference, like what the Euclid only error bar looks like relatively. And the distance to the blue and the red curve correspond to what happens when you add the CMB lensing and when you add the full CMB information and all cross correlation. So it gives you a more visual, really. You see the shrinkage of the error bars. A lot of people interested in large scale structure like to see things in terms of. There's one key quantity that interests large scale structure people is the figure of merit of the dark energy, which is when you plot the ellipse of confidence in the W0 WA space. It's essentially a measure of the inverse of the inverse of the area of the ellipse. So the bigger the figure of merit, the tighter the constraints are. And you can see the improvement as you go from the three things are like Euclid, and again, it's always the same. Euclid only, Euclid plus CMB lensing, and Euclid plus all the CMB. And you see the progression in the numbers, which especially in the very the tricky case where you free basically everything. In those tricky cases, you really see the improvement by adding the CMB information. And that's just to just quickly flash it on the screen. That's the constraint on the parameter gamma, so the modified gravity parameterization. There's since I want to, since this is a workshop about synergy, and I want to emphasize, it's kind of bouncing back on the comments of Iggy, which is what about the other way around, right? Like, okay, so this is kind of from the perspective of Euclid, because this was a Euclid paper. What can CMB bring to Euclid? But you'll notice, you might have already thought in your head, what the hell is tau doing here? Because if you trusted what I just said, this should be the improvement on tau from adding CMB to Euclid. But Euclid is a large-scale structure survey, which has almost basically nothing to say about tau and the reionization epoch. And it turns out that actually this particular column is unique in the sense that it's the reverse of what I've been talking about so far. Namely, it's the improvement on CMB-only constraint that comes from adding the Euclid on top of it. And for this particular case of okay, that's I chose the best table, which is like adding on top of CMB optimistic Euclid. You get quite a tremendous improvement, like factors of 2 to 3 essentially, or even 4 on the error bars on tau, and that's very interesting for CMB people, because when you use just the CMB, you have quite a big degeneracy on the value of tau and the value of sigma 8 or AS. It's the same. Like you really have the reionization damps your CMB spectrum, and but if you start from in the early universe higher up, you can compensate the two. So you can have more damping, but you can also start from a higher value of scalar perturbation, and it fits the data the same. So that's the CMB only situation. But then Euclid comes along and puts like this kind of error bar on sigma 8 or on AS equivalently, and immediately, yeah, you can shrink significantly your constraint on tau. How am I doing on time, Kostas? Just okay, perfect. That's. This is one of my last slides. I just wanted to mention, maybe some of you already maybe have the question in mind. Why didn't you implement this and that and this and that? That's I can deflect the question by saying, oh, we just follow what the IST did. So we, but I need to point them out what area of improvements are, what the area of improvements are, and they are actually worked on right now in the collaboration to produce more realistic forecast. For example, the distribution of galaxy and the uncertainty on the photometric redshift estimation, they were there, but they were not, the parameters were there, but they were not considered as nuisance parameter. They were fixed to the fiducial value. And that's somewhere where also the CMB could help to help constrain more those, if we let them go free, that could help too. The galaxy bias was linear, like scale independent and everything. So of course, especially on nonlinear scale, we kind of want to go beyond this kind of assumption. There was the idea that the spectroscopic wasn't correlated with everything. Maybe we want to explore what happens when it correlates with the rest. BAO reconstruction was not there. Magnification bias was not there. DR's effect in the galaxy clustering were not there. And also the one big point is like the covariance was fully Gaussian. There was nothing else than Gaussian terms. But we know that with Euclid, there's going to be additional non-Gaussian terms in the covariance, especially, for example, the supersample covariance. And all of those will make the focus better. And all of those will most likely highlight even further the improvement that you can expect from adding the CMB. In terms of future perspective, yeah. So on top of those areas of improvement that I said before, we want to move on to extended model. As you saw, we really explored the most basics of basics modified gravity model, the gamma parameterization, which pretty much everyone agrees it's not really physically, it doesn't correspond to any really physical model at all. So we want to move beyond that. We want to move to more realistic forecast, like I said, or accounting all the stuff we left on the side, but also more practically moving away from Fisher forecasts, because there's all those issues about posteriors that can be non-Gaussian, especially in models where you start freeing up more and more parameter. You can expect your contours to not be nice ellipses, and Fisher is not going to be able to tell you that this is happening, and it might impact your forecast. So we want to be ready for this, and we want to move away from Fisher forecast and go to MCMC. Then, of course, in terms of perspective, right now we are currently working with the IST to implement the CMB in the cosmological pipeline. So we can reasonably expect that when the data is there, we will be able to immediately analyze it in addition, jointly analyze it with the best CMB data that will be available at that time. But we also have in mind to separately, maybe from this pipeline, look for different ways to combine Euclid and CMB probes. And among those, there's like the SZ effect that I mentioned, which is not in this analysis so far, this CIB I mentioned, and also maybe the effect of superstructure. That's something that maybe you have heard, and I don't know if I have like 1 minute or two to Costas to maybe mention it. Okay, yeah, there's this one thing that there was one thing in particular in terms of perspective that I'm interested in, like really a focus on the ISW effect, because so the ISW effect is really a good probe. It's something that really probes the evolution of the time evolution of gravitational potential. So it's kind of unique in this sense. And it could help a lot when it comes to constraining dark energy model and gravitational modified gravity. This is here a review from 2018 that made a catalog of all the measurement of the amplitude of this ISW effect. And you'll notice that in terms of this is the signal to noise ratio. It's nothing to write poems about, but even with this kind of low signal to noise ratio, relatively low, because like lensing or this kind of stuff, it's like 10 sigma, 20 sigma, who knows. Even with those low signal to noise ratio, if we jump back to 2017, 1 month before there was this gravitational wave event with its electromagnetic counterpart that kind of put the nail in the coffin of a whole range of modified gravity model. 1 month before that, there was using the best ISW measurement. There was already these authors were already able to exclude a large part of the Galilean theory, thanks to a very, very distinct signature in this cross correlation spectrum, which turned out to be negative in those models. And since we observe it to be absolutely not negative, this was already there, able to preemptively remove a lot of those models. So we can expect there's some things to be explored in this cross correlation between CMB and large scale structure. You also notice maybe that those numbers are suspiciously skewed in one direction. They tend to be kind of all a bit more than 1. So a value of 1 would be what lambda CDM predicts. And they all tend to be not significantly, but still tend to skew a bit towards higher value. And this is kind of mirror in another way to measure the ISW effect, which is to simply look in the sky for the biggest structure you can find, and at the position of the structure, you like cut out pieces of the CMB that you stack together, and you hope to basically raise the signal to noise ratio of the ISW effect by looking really. It's not a 2-point correlation function anymore. It's like straight up in real in the sky in real space. You just stack up patches of the CMB. And throughout the years, the value of the amplitude of the ISW effect measured this way tends also to be like quite significantly skewed in the higher value of this amplitude value. Again, the lambda CDM value is here. This blue band corresponds to the traditional cross correlation way, the 2-point function that I was showing in the previous slide. And those data points with error bar correspond to this more direct measurement of the ISW effect of superstructure. So this is also something we are very interested in, and there might be something to dig deeper, because with Euclid you can expect to shrink this error bar. Like in terms of structure to stack, you can expect orders of magnitude more structure to stack. So you can expect to shrink those error bars significantly. So there might be something to really interesting to dig in looking at those superstructure, and we hope to prepare for that as part of Euclid. And yeah, I guess that was my last point, and I thank you very much for your attention, both you in person and remotely.
So we have time for questions. Anything on Zoom?
I think David is raising his hand.
David, go ahead, ask your question.
Thank you. So I had a question. If you can go back to one of the first slides where you were showing the way you were computing the Fisher matrix.
This one maybe, or
right, yeah. So so in your case, you're using a set of power spectra as your data vector, but you're including both the dependence on parameters of that data vector and also the covariance matrix. Is that right in these two terms, or did you skip one of them, or yeah, did you include the two terms?
So for the sake of completeness, in like the IST paper, and I think we also mention it in our own paper, we basically adopt two. Okay, in our paper, we discuss the 2 point of view. Like either you use as observable the ALMs.
Yeah.
You consider yourself as if you were using the ALM. And since the ALM are considered to be Gaussian of mean zero, the right term disappear, and you only get the left term, and it looks like the standard derivative of CLs times covariance times derivative of CLs, roughly speaking. And then we also mentioned that the other point of view is to use really the CLs as observable. But then actually I know a lot of people use the CLs and then they directly take this formula and they mumble a few words about, okay, we keep the covariance constant or whatever. But actually I think the correct reasoning is to say, okay, if you take the CLs as observable, then you have to remember that they do not have a Gaussian PDF. They follow a Wishart distribution. And if you go back from the beginning of the formula, the definition of the Fisher matrix, and you rederive all the computation, you arrive actually at the same formula as the ALM, which makes sense. Like there's not more information in the CLs than the ALM. So you end up with a term that looks like the rightmost term. If you adopt the CL's formalism and do it properly, there is no derivative of the covariance that appear. Only derivative of the.
Great. Yeah. So I just wanted to figure to make sure of that, because that's many people spend a lot of time trying to calculate the left term, and actually it's even incorrect to do it, right? So yeah, great, cool.
Exactly. Yeah, I agree. Good.
So I have one question. So can you combine the full actual Planck likelihood with Fisher?
That's a very good question. Turns out that I have a backup slide. One of the things that we actually did, I think it might be on one of my slides very briefly. Yeah, at the bottom, I mentioned the fact that we didn't just do Fisher forecasts. We also said that, okay, combining Euclid with CMB data, but we already have some CMB data. We have Planck. So what about using a Fisher matrix from Euclid that we compute the way we described and try to combine it only in the most basic way, so assuming independence between the two experiments. What if we combine it with real data by just taking an MC-MC chain and fitting the posterior and making a pseudo Fisher matrix out of it? And I think I have them in backup. In any case, it's essentially, the idea is that you take that's in blue, that's an MC-MC chain, and like you fit an n-dimensional Gaussian on top of it, and you use that, you invert it, and that's your pseudo Fisher matrix, and then you can just add it to your Euclid Fisher matrix, and this is essentially all the results we can make, because that was all the available Planck chain at that time. And when you put them side to side with the Fisher forecast, it's surprisingly, the trend are exactly the same, and the number are surprisingly similar, even though there's quite a lot of different things happening in the analysis. So yeah, we can do that, and we tried it for completeness sake, let's say.
Okay, so thank you, Stéphane. Okay, Agi, one more.
So, then on the Skovats paper that you showed, I missed that paper somehow. So this superstructures. So the interpretation of this is that in the direction of voids, the potential decay is even faster than the CTM. Yes, that's the.
Yep. Okay. Yep. Exactly that. Supervoids somehow create a more intense ISW effect, which would indicate that the phi dot is bigger, or there's some fishy stuff happening. If my only criticism of this is that they tend to go the simulation way to compute the compare, because they have to compare to some expectation, and they don't do any theoretical calculation. They go straight to n-body simulation way. And I suspect maybe the way you do the ray tracing in your simulation might possibly affect your prediction. Maybe they're not a big factor, but I always wondered if there wasn't a way to do this purely analytically. But maybe it's complicated. Yeah.
Thank you.
Okay, so thanks, Stéphane.
Yep.